So the last topic that we need to talk about here in our solubility unit has to deal with the separations in group 2 and group 3. So if we look at the group 2 and group 3 sulfide precipitation, this is going to be our last topic that we're going to look at in this solubility unit. In group 1, we said that these cations will precipitate, group 2, these sulfides will precipitate as a sulfide in acidic solution. The difference between the group 2 and the group 3 cations is that the group 3 cations will precipitate as sulfides as the pH is increased. And the pH at which of these sulfides precipitate is going to change when we change the cation. Remember that a precipitate forms when Q is greater than K. If you look at a KSP table for all of these metal sulfides, the KSPs are a different value, so they're going to precipitate out at a different pH. The reason we save this analysis to the very, very end is because there's some pretty complex chemistry that's happening in these solutions. So the first thing that we need to ask ourselves is, how do we provide a sulfide solution? Because if you look in your lab procedure, sulfide ion or sulfide solutions are not used. Okay? They're very, very foul smelling. They smell like rotten eggs and sulfur, and the chemistry is absolutely awful in solution. So it's like, how do we get around this, and how can we do some calculations and analyze these sulfide precipitates in solution? So the source of the sulfide ion is thioacetamide. And thioacetamide is CH3CSNH2. This produces a saturated H2S solution which has a concentration of 0.10 molar when we have this saturation point. The great thing about thioacetamide is when you heat it up to, I believe, around 70 to 80 degrees Celsius, it begins to break down. And one of the products that it forms is H2S. So what we can do with this particular solution is we can heat it up to a certain temperature that we need. It will break down to form H2S in solution. Remember that H2S is a weak acid. So I'm going to skip over to a new page here. And if we look at H2S in solution, it's a weak acid. And more specifically, it's a weak diprotic acid. So H2S will break down into H plus ions in aqueous solution plus HS minus in aqueous solution. The K1 for this particular expression is 9.5 times 10 to the minus 8th. In addition to having this equilibrium, our HS minus ions in solution are going to be in equilibrium with H plus S2 minus. The K2, if you remember back from the acid-base chapter, the second dissociation constant is typically much smaller than the first one. We're going to say that it's small enough, or very, very small, that we can essentially ignore that step. So our K1 expression is going to be the concentration of H plus times the concentration of HS minus divided by the concentration of H2S, and that equals 9.5 times 10 to the minus 8.